Okay, so I welcome you all. Welcome all intellectual adventurers in today's meeting. So today I'll talk about error estimation in computation. So today's talk might seem a bit very theoretical, but still it will give you some flavor that just writing a program based on algorithm is not sufficient. You should also have an estimation of the errors that you will eventually have in your program, because if the errors are too much, then the results of your program are not that trustworthy. So errors are something that you at least should be aware of, and should be and this should give you flavor, because this is not that in details, but this should at least give you some flavors that errors are something that you should not be careless about. Okay, so this is the these are the topics that I will discuss today. I'll first introduce and motivate you, like what are errors and why you should be at all concerned about these things, and then how do you compute errors, and also about their propagation. So how do the errors propagate? I mean, perhaps you know about it already, but still, just for the completeness sake, I will say about this as well. And then how do we represent real numbers on a computer? Again, I will not go into too many details, because representing real numbers will also involve representing that number using the binary numbers 0 and 1, which I will not talk much about, because perhaps that's not useful for our discussion. Perhaps that can be talked about in some other discussion. Okay, so first, let me say about let me introduce you about this and motivate you a bit. So we know that the numbers are very important in physics. All sorts of theoretical predictions and also let's say experiments will produce numbers. Okay, so for example, Einstein said that in the presence of sun, because he had the mass of the sun, so he predicted that that because of the presence of mass based on its general relativity, the light ray will bend by an angle of about 1.75 arc seconds. And Eddington, while he did the experiment, found the observation consistent with what Einstein gave predictions of. Okay, so that's one thing. And when Higgs and other persons, they talked about Higgs boson, that they told that the Higgs boson will have mass within this range, or will have this mass. And when CERN actually discovered that Higgs boson around in 2012, so they also give the error bound, so, and also the sigma value. So they give the mass value of the Higgs and also the error that the experiment will have. Okay, so the point is that just quoting the numbers from an experiment, and as we will see, also in the case of just quoting numbers from computation from your program is not sufficient. You should also be aware of the error that you will introduce. Okay, so let me so although I've talked about two examples already, one from general relativity and the discovery of Higgs boson, but let me give one more example. So let's consider the classical example of photoelectric effect. So using the equations of photoelectric effect as given by Einstein, because, okay, let me say a few words about the photoelectric effect as well. So this happens when a photon of sufficient frequency falls on a metal. So it does not depend what is the intensity of the radiation, but it depends upon the frequency of the photon that falls upon the metal. So if the frequency is sufficient, then the electron would, or rather the photon would be able to eject the electron out of the metal. That depends upon the work function. And the rest of the energy that the photon will give to the electron will be seen as its kinetic energy. So then you can estimate the maximum kinetic energy by applying the negative potential. And based on that, you can estimate H over E, as was done by Robert Millikan in this paper. So since he already knew about the electronic charge using his own oil drop experiment, so he could estimate the value of H from his experiment. And the value of H he found was equal to this 6.56 with 3 significant digits. But the errors were also given. So now you compare this with the modern H value. So this has 3 10 significant digits. So this value is very, very accurate, and it has also a lot of precision. So I'll talk about so accuracy and precision are not the same things. They have a difference. So, and we will talk about that part also. So thus, errors are very important component of any experiment. And for today's discussion, errors are I would also add, errors are very important component of any computation as well. Because, for example, you may not be aware of it, but since so for example, if you evaluate integrals using Python, so Python will give you the result, but it will also give an estimate of the error. So again, I mean, I cannot emphasize it enough that computation is not enough. You also have to have an error bound, the estimate of errors on the numbers that you have obtained. So if you estimate errors, you are more confident about the numbers that you have obtained, and it can also help you understand or design better algorithms. So maybe some algorithm or maybe some steps are there in between that can help reducing the amount of errors that you will have. So as we will see, because addition and subtraction will cause more errors as compared to just the division or multiplication, okay, as we will see. So, and it will also help us understand where the errors are relatively large and are sensitive to various parameters. So for example, if you have an integrand involving sine alpha x, for example, with some other function, so if you take alpha large, then the oscillations will be too much. So then the convergence properties of the integral and the error that you will introduce will depend on the value of alpha strongly. Okay. So now let me talk about errors. Okay. So now let me talk about errors in computing and their propagation. So how do we calculate the errors and how do they propagate? Because a quantity may depend upon some other independent variables, and those independent variables may have their own errors. So the errors in those variables will be reflected in the error of the quantity that we are trying to evaluate finally. Okay. So first, what are errors? So for that, so let me first introduce the idea of the exact value of a quantity. Let's say you have some quantity, and I denote the exact value of the quantity to be x. So let's say the length, for example. I mean, so of course, the length, we don't know a priori what is the exact value. But then, for example, you know square root 2 whole square. So you know that square root 2 whole square is 2. So that's the exact value of square root 2 whole square. But then that's not the value that Python will give you, mind you. Okay, so I'll give this example next. So, but Python will only give you an approximate value, because if you say about square root 2, because it has non-terminating, non-repeating, it's a non-terminating, non-repeating decimal. There is no pattern in the numbers. So for example, 1.414. So, but the numbers that follow this 4 will have no pattern. So in principle, you should have infinite number of digits in square root of 2, which is not possible to store in the computer. So that's why the computer will always give you an approximate value of square root 2, for example. Okay, and accuracy describes how close we are to exact value. So we know that square root 2 whole square is 2. So that's the exact value, but this is not Python will give. So Python will give some value close to square root of 2 square. So in this case, we know what exact value is, but it may not be available to us all the time, because if we are doing some new computation on your computer for the first time, you don't know what the results are going to be. So in that case, the exact value is not known. And the related idea is precision. So accuracy and precision are not the same things. They are different things. So precision depends upon how many significant digits you are using in your mathematical operation. Okay. So let me give you an example. So let's say you have a quantity x. The exact value of that quantity is 2.3432, for example. And let's say you obtain the approximate value of x through two different algorithms, through two different programs. One was this 2.32 and one was 2.52323. So as you can see this, that the value x1 tilde is close to x, is closer to x as compared to x2 tilde. So I would say that x1 is more accurate as compared to x2. Okay. But then the later one, this x2 tilde has 6 significant digits as compared to x1, which has only 3 significant digits. So it's more precise. So these are two different things. Precision and accuracy are not the same things, they are different things. Okay. So then an inaccurate result arises because of many types of errors. So one is the human error, because, okay, so in the present context, I'm not talking about any experiments. I'm only exclusively talking about programming, computations. So one error can be that, let's say you had a very complicated expression, and then you introduced an error because you programmed the wrong expression. So that's a human error. The other one is approximation error, which I will talk about next. And the third one is round off errors. So approximation error. Okay, so let me talk about the approximation error now. So let's say you want to estimate the value of exponential x using a Taylor series. So you know that this is an infinite series, and in principle, n max should go to infinity for you to give the exact answer. But then in order to do that, you have to consider infinite number of terms, and that's not possible for to do in a program. So what you do then, you terminate the series at some n max. So as I just said, in principle, this should have been n max going to infinity. So by doing that, you are chopping off all the terms that are coming from n max plus 1 to infinity. So for example, if you take n max equal to 1, then it will give you fx equal to 1. But then that's not the very good approximation, because let's say if you take x equal to 2, then e square is about 7.2 something. But then 7.2 is not 1. So n max equal to 1 will not be a very good approximation. Oh, I'm sorry. N max equal to 0 will not be very good approximation. And similarly, if you take n max equal to 1, then you will get 3. That's also not very good, and so on. So if you keep adding number of terms, the approximation will become better and better. So thus you can see that the function fx present here, though depends upon x, but also depends upon the value of n max. So the larger the value of n max you choose, the better the approximation becomes. So this is visible from this plot. So thus in principle, if you take larger value of n max, you will get better and better approximation. The value that you will get will become closer and closer to e square. I mean, for at f of 2, because this is exponential x, and if you put x equal to 2, you will get the value of e square. So okay, so this is how you get this. Get this plot. So I have included the whole Python code here. So what this part is doing is, so this first part is evaluating these terms order by order. So let's say so what is this series? 1 plus x square over factorial 2, x cube over factorial 3, and so on. So this function evaluates those terms separately. And this term and this function evaluates sum of first n terms. Okay, so first n terms. So and I'm just taken a for loop on this n max, and this part does the plotting. So this is what you get. So as can be seen that till let's say 4, 6. So let's say this is 6. So at 6 there are some errors. Of course, it depends upon how accurate you want your results to be. But at 8, 10, so the errors are very small. So maybe they're of the order of 10 power minus 3 or 10 power minus 4. So that's a difference. And that will also lead us to something called as the absolute error. That will come next. Okay. The next is the round of errors. Okay.
I have one doubt in the previous slide.
Okay.
Maybe I would just want to check again that code. So here you have written that if order is less than 0, then you will exit the code. Then order is equal to 1, 0, then it will be 1. Else it will be 1.0. And for the next one, you have written if order is equal to 0, then it will be 1.0. Else it will be 1. So why it is like that? 1.0 and 1 for equal to 1 and like greater than 1.
Yeah, this could have been 1.0 as well, because you have to eventually take a for loop, because you will sum over various number of terms. Okay, so I could have reduced the size of the code. I could have written if here and else and answer equal to 1 in either of the cases. But
Yeah.
if yeah,
So both of the one are same. One
yeah.
on one in this code. Okay.
Yeah, they are the same. Okay. Yeah. This can be an improvement on the code. Okay, thank you. I can improve the code that way. Okay. So as I said, that this type of error arises when we use floating point numbers. So for example, square root of 2, pi, pi over 2, e, for example. Okay. So because these numbers don't have infinite precision, some information is lost, as we will see next. So let's consider, for example, this code, or rather this number, or that we want to do this computation. Square root of 2 square minus 2. So what is this? You all know. This is just 0. So in this case, we know what the exact value is, but we may or may not know the exact value in all of the cases. Okay. So, but if you evaluate this through this Python code, then let's say x is equal to square root of 2. And if you square and subtract 2 from it, you should get 0. But this is not what you get. You will get this number. So what is happening here? So first thing is the error will, okay, so let me explain what is happening here. So first thing is, so the problem starts from the first part itself, because Python won't be able to store square root 2 exactly, because it will be an approximation for square root 2. That won't be the case for 2, because it can store 2 exactly. But so because it is not able to store square root 2 exactly, and when it squares it is introducing an error. And when it is subtracting it from 2, or rather when you're subtracting 2 from it, you are again introducing an error. So that's why you are not getting that answer. And you can check. Perhaps I will also show that in the end, that if you square 2, I mean that if you square root of 2, then it is not exactly equal to 2. And you can also check it's not that difficult. So now imagine what will happen if you multiply this with a very large number. So theoretically, this should have been 0. Okay, this thing should have been 0. And if you had multiplied it with 10 power 10, 10 power 20, 10 power 30, whatever, you will always get 0. But then this won't happen in the case of Python, because if it is this quantity, and if you multiply it with, let's say, very large number, the error will get multiplied. It will not be 0. So it gives at least a flavor that that you should be careful while doing computations. So you should not do computation just blindly. You know the algorithm and you will just program it. So you should be careful about how you're programming your algorithm, and at least a feel for it, or at least some insights of it, that these are the places where very large errors might creep in. Okay, and thus these kind of errors cannot go even if you run your calculations even for longer time. So this is different from the previous case. So in the previous,
Rahul, may I ask something?
Yeah, please go ahead.
So as you said in previous slide, because of that non-repeatability and non-periodicity of square root of 2, so we are actually end up with some non-zero numbers. And when you square it, that again add on to the errors. So just because the computer cannot store the infinite numbers in its memory, is it?
Yes.
So here again you are telling if you multiply this number, so that residual part will get multiplied with whatever bigger number we are trying to multiply. So that will further add on to the error. So is that the reason here also? Even if you will keep on running your calculation, it doesn't affect actually that error.
Yeah, because you can see here. So I mean that the time does not really depend. The time does not really depend upon it. So even if you keep calculating your error for longer time, the answer will not change.
Okay. So it is entirely lies on the limitation of the memory of the computer.
Yeah, because in principle, Yeah, in one way it is, but that's not the right way of saying it, because in principle you should have in infinite bits for it. So if you want to score like store a square root 2 on your system or rather in a variable, you should have infinite number of digits in it, and that's not possible.
So then I have a small clarification. So let's imagine I have a supercomputer which can actually store infinite number, let's suppose infinite bit. So in that case, the running time of the code will not have any impact on the error bar.
But perhaps in order to store an infinite number and then doing the computation may increase your time. But then you are assuming that the computer can store that very large number. So maybe in that case, it's possible.
Okay, I got it.
Thank you. Because actually I did an experiment today. So I did some experiment on the computer. So first thing is, in order to, so what I was trying, I was calculating various powers of 100. I mean, I should have had that, I should have that code maybe somewhere on my system. But anyway, so I was trying to calculate various powers of 100. Like 100 power 100, 100 power 200, 300, 400, 10,000, 100,000. Yeah, very large numbers. And then there's a function in Python that calculates the amount of space it takes.
Okay.
So when the number was becoming larger, the time it was taking to calculate the space was also increasing.
Okay.
So perhaps it depends. So so this is my guess. I mean, I'm not so completely sure about this, but I think this is what should happen, that if you have very large numbers, so let's say square root 2, you take infinite number of numbers, it will take infinite time to do your computation.
Yeah. So just to calculate every order.
Yeah. It will take infinite time, and that's not very useful.
Yes. Okay.
Because
discuss on this.
And also and if you think of about and think about it practically, your experiments will also not be able to give infinite number of digits for any given experiment. They will have, let's say, some 10 significant digits, maybe 15 in some cases, but not infinite number of significant digits, and that you don't need anyway.
Yeah.
So the moral is that you should be careful about how you are manipulating various quantities in your program or various numbers, and especially when you're subtracting. So this is the place where
so let me ask you another question, if you allow. That suppose people are calculating the information paradox in the black hole. So how are they calculating that microscopic number, the number of that is what they are calling it, Shannon entropy, or I don't know what is that entropy, I'm forgetting. So that number of microscopic degrees of freedom. So a priori, how are you going to assume that how many of them are there, and how they are calculating whether information is going to be lost or it will prevail?
No, but are you talking about theoretical computation or computation using computer?
Computation using computer.
So because the number of microstates are very large. So one way is one very simple rule of thumb is, if you have very large numbers or very small numbers in a system, just try to scale up so that they are of the order of 1 or 10 or 100. Then the calculations become manageable. So first thing is this: if you have somehow very large numbers in your calculations, just try to scale up.
Scale down. Okay.
Scale up or scale down.
Okay.
So that that is certainly I mean, so when you're talking about large or small numbers, that's a different story. So that's the so that's underflow or overflow. I'm not talking about that right now. So that's a different thing.
Okay. I was just curious about how they are calculating. If this computer has this much error bar just to calculate the square root of 2, so however powerful my computer be, that is certainly not supercomputer or quantum computer. So how are they going to manage that large degree of freedom in this computer?
No, but
that's what I was just curious.
Okay, I understand this is a valid query, but then you're also so this is the very important moral. You're just not programming blindly. You have an idea where errors can creep in.
Okay.
So especially
Many
when you subtract quantities, subtract or add quantities, that's the most erroneous place in a program. So you should be very careful on that place. Otherwise, multiplication, etc., do not introduce that much error.
Yes. Yeah, the last statement you made, that was, I think, more important statement. As a theoretician, you need to know where I probably can get more error.
Yeah, true.
And what I am supposed to get more error. Okay.
Yeah, and I will also talk about this part. So through one example. So I will talk about catastrophic cancellation. So in the forthcoming slides. Okay. So one related aspect is absolute and relative errors. So again, let the exact value of a quantity be x, and you will see the utility of it. And let x tilde be its approximate value, then the absolute error is this. So notice the way I've defined is because I have not put absolute values here. So this quantity can be either positive or negative. Okay. So as an example, let's take quantity 0, whose exact value is 1.000, having 4 significant digits. And the approximate value is this. Then delta x 0, very simple, is equal to minus 10 to the minus 3. Okay. So I mean, we are not really interested right now in the sources of error. So it can be because of the uncertainties in the input data, because you may also because a computer program will also be able to take your input data from a file and then do some analysis to it. So there can be problems in that place. Okay. And then because of the various steps involved, the errors may get the errors will get propagated and will add up over the computations. So various computation involving various computations, the error might get accumulated. So that's not our concern right now. So many times we don't know the exact value. So we define a useful quantity called as error bound. So this is the absolute error. So error bound is the modulus value of this. So this is the upper bound on the absolute of absolute error. So this is how you define it. So if you do that, then you can show that this is equivalent to saying that the true value or the exact value of x lies between the approximated value plus or minus epsilon in this way. So error bounds are very useful to give. So if you have error bounds, you know how much can you trust your results. So error bound are very important to be calculated from the most of the time. So if you talk of the integration, because this is what I'm also involved with. So if you talk about integrations, so Python integration methods will always give you error bounds, absolute error or relative errors. They will always give you that number. So now, before proceeding further, let me take one more example. So let us have quantity 1, whose exact value is this, and approximate value is this. Then delta x is equal to this. Okay. So, I mean, it feels like that in the quantity in example 2. So this quantity, this approximate value is closer to this as compared to this being close to that. But then delta x1 is minus 1 in this case, and this is very small. So this motivates us to introduce another concept called as relative error, because it seems that the two comparisons are not fair, because the value itself here is very small as compared to this. So this motivates us to introduce a new concept of relative error. Okay. So relative error is defined to be this quantity divided by the x, the exact value of the quantity. So if you do the same computation in this case, you will get delta x0 the same, because the x0 is 1, but this is now 10 to the minus 9. So this suggests that our feel or intuition was right. So in that way, this is closer to x1 as compared to this being closer to this. Okay. So now let me talk about question.
Yes, sir. Not question, some clarification.
Okay.
In the second example, should there be one more 0 in x1?
Wait a second. 3, 3, 3, 9. ठीक तो एक मिनट Oh, yes, yes, one more zero will be there. Thank you. Thank you. One more zero will be there. Okay, so now a given quantity, let's say the quantity that we are evaluating using computer may depend upon various variables. So maybe you can have, let's say, the value of, or let's say y equal to mx plus c. Okay, so it depends. So for a given x value, it depends upon two parameters, let's say m and c. Okay, so m and c may have their own errors. X can itself have its own errors. So we want to know that by knowing the errors in two variables, let's say x0 and x1, how to estimate the error in the dependent variable y. So let's assume that they are given by the sum or product, because the answer will be same in either of the cases. And again, the exact value of the independent variables, these ones may or may not be known. Because, so let me reiterate. So for the case when we were testing what is square root of 2 square minus 2, in that case I know that the answer is supposed to be 0, but this may or may not always happen. Okay, so now our objective is to estimate the bound on y, the error bound that was shown before, that it is the upper bound on the absolute of the absolute value. So assume that you know that the error bounds on x0 is epsilon x0 and x1 is epsilon x1. You can very easily show some by some trivial math that this is equal to this, that this is equal to the sum of the two error bounds. And this will be true even when you take plus or minus. It will be true in both the cases. And if you take division, for example, you can easily show that but by the way, there is a difference between this delta and delta, as I showed in the previous slide, because this is the absolute error, this is the relative error. So here in this case, for the division as well as in the case of multiplication, you can show that the bound on the relative error is given by the sum of the relative errors on these variables x0 and x1. Okay, so this gives you an estimate. Let's say you know that a quantity x0 will have this much error, quantity x1 will have this much error. What is the error that you will introduce, that you will have on some other quantity that depends upon x0 and x1? Okay, so now let me talk one dramatic example of catastrophic cancellation. Okay, so now consider a very special case of subtraction, because we've also talked about subtraction when a and b are very close. So this is the same as square root of 2 square minus 2. Okay, so of course in that case they are exactly equal, but then and this can also not be done on computer, but then consider a case where the numbers are very close to each other and we are performing subtraction. So in that case you can show, I mean, I'm not demonstrating it, you can do it for yourself. It's not that difficult to do. So, and this assumes that a is approximately equal to b. I've taken this approximation here. Okay, so this is the relative error bound you get. So now, even if the relative errors on a and b, which is this and this, are very small, because of this factor in the denominator, the error will shoot up. They will become very large. Okay, so for example, if you take a to be 1.25, ex, the error bound on x 0.03 and y also 0.03, and the quantity b to be this, and you are now calculating the relative error bounds on x equal to a minus b, it is found to be 122%. So that's too large. So that's why it's known as catastrophic cancellation. So errors will in general shoot up when you are subtracting quantities of the same order. So you always have to be careful about it, that if you are subtracting quantities of the same order, then be careful, or maybe you should be or should try to find out those places where such cancellation is happening, because you may get completely nonsensical results if you're not careful about these error estimations. Okay, so it usually the case that multiplication and division, as can be shown mathematically, will not cause that much of a trouble. So although it is happening in the case of subtraction, this won't be the case when you do multiplication or division. Okay, so okay, fine. So I mean, in my personal case, I have faced this problem over and over again when I was calculating angular power spectrum. So because angular power spectrum has a spherical Bessel function in its integrand, and they oscillate like wild. They oscillate wildly. So and the sign keeps on changing. So because you now have to add very quantities of the same order but with positive and negative sign. So this sort of things will appear, and that's why it will have very slow convergence, because the Python program is told that do not stop until you achieve this sort of error bound. So that's why these sort of programs, these sort of cases, when you have a spherical Bessel function in the integrand, they converge very slowly. Okay, fine. So now let me talk about the error propagation. So previously I talked about just the simple cases of addition, multiplication, division, etc., etc. But then you can also, for example, square something. So maybe you can exponentiate a variable, you can take a log of it, you can square it, you can have a polynomial dependence. So maybe let's say you have this sort of very non-trivial dependence. So here alpha, beta, and gamma are appropriate parameters, dimensional for parameters, so that the dimension of LHS and RHS match. Okay. So then the absolute error in Y can be written as this. So this is the expression you obtain using Taylor expansion. So what you do, you will expand this function about X. So and you will perform a Taylor expansion, and then you can show that the absolute error in Y can be written as this. So what does it mean? That the that this delta X is very small. Of course, the error has to be very small, so that I neglected any higher order corrections. But the important thing that you can see here is that, so the error that you will see in Y finally will depend upon the derivative as well. If the derivative is large, although this delta X can be small, the error in Y will become large. Okay. So, and now if you want to consider the most general case in which Y depends upon many variables, x1, x2, any number of variables, x1, x2, and xn. So then you write in that way, and let's say I denote these numbers as just vector x. Okay. So then again you can show by multivariable calculus. You must have seen it, I'm sure, by using the multivariable Taylor expansion, that delta Y, the error you introduce in Y, is equal to this. These are the partial derivative of f with respect to xi, and also the relative error are given to be this. So these are the most general cases, and then using these results you can show, or rather you can derive the results that we have obtained before. So you can ask what happens when you add two numbers, let's say x0 and x1. So using these results you will get those answers. Okay, so now let me turn to a very important idea of representing real numbers on a computer, because eventually you will perform all your computations using real numbers, and the way they are stored or being operated on will decide the error that you will get finally. So as we know that the computers store numbers in the binary form, in the form of 0 and 1. So and I'm sure you must have done this exercise, how to convert decimal number into this form of 0 and 1 in the binary form. So Python integers have unlimited precision, so we don't have to worry about them. So you can evaluate as large integer as you want, but this is not the case with real numbers. So our main concern here would be the real numbers. So a given real number is stored using something called as floating point representation, so which has the following form. So this is a sign, plus or minus. It can be positive or negative, and then it has the mantissa, and then it has the exponent. So for example, let's say it has plus sign over here. This is the speed of light, approximately the speed of light. I've not taken it fully, because it has been evaluated till at least 6 decimal places. This is what I'm aware of, or maybe more than that. So, and this is the exponent. Of course, it will depend upon the unit you are considering, but then you will store a number in your code, for example, and this is the value of h in electron volt second units. Okay. Sorry. Sorry. Okay, then. But then the computers can only store finite number of bits. So if you talk of square root 2 and pi, it has this sort of expansion, and pi is this sort of expansion. So you will have to, in principle, have to store infinite number of digits. So thus it is impossible to do so. Okay. So computers can only store finite number of bits for these numbers, for floating point, for a given real number x. So now there are three ways of losing precision. So now we have come to the point as Gyanti talked about before, or while we were discussing. So one problem can be overflow, the other is underflow, and the third one can be rounding for decimal numbers. So because you are not able to express these real numbers exactly, so that will also cause a problem. So overflow, underflow are different problems, but that's also another problem. So so it turns out that so usually you have 64-bit computers these days. So earlier, maybe about 10 to 15 years ago, or maybe more than that, you used to have 32 bits computer, but now almost all of the computers are 64 bits. So the computers will store any of such numbers in 64 bits. So this allows us to represent any such number in this range. So if any number goes outside either of these ranges, it will be it will give you either infinity or zero, as we will see next. So your number that you are trying to, your real number that you are trying to represent on the, or rather store on the computer, must be within this range on the negative side, and this on the positive side. And the number of significant digits are found from the mantissa. This is pretty much straightforward. And I will also talk about this quantity called precision or machine precision later. So let me now explain what I showed in the previous slide pictorially. So if you have any number that goes beyond this quantity 1.83 10 power 308, it will give you infinity. And again, if you go in this region, let's say in this region, it will again give you minus infinity in this case. And again, if you have any number in this region, it will give you 0. So for example, let's say we talk about underflow. So I've already considered a very large number, let's say this one, because dot means that I'm taking it as a float. Okay, so it's not an integer, it's a float. So what I'm doing here, I'm multiplying this quantity again and again by 2. So when I first evaluate this, so here I'm multiplying this quantity by 2, so I get this. I'm multiplying then this quantity by 2, so I'm getting this. And as soon as I cross, so because it would be about 19, so some quantity of this order, it would be about 1.8 10 power 308. So as soon as this reaches this quantity, it becomes infinite. So because it has gone into the overflow region, it will give you infinity. So the other would be underflow. So here also I've taken a very small number now. So now I will just keep halving it. So whatever this number is, I'll divide it by 2. I'll get this again. And after reaching some certain point, let's say this one, so this will just show 0. So this is the meaning of overflow and underflow. So one way of getting around this is to never use very large numbers. So if it is possible to scale up or scale down your calculations in such a way that you can take out very large number in front of your expressions, this is what you should do. You should not program that number in your computer blindly. Somehow you should sit and work out some math and then try to take out that number ahead. Okay. So now one very useful idea is the machine precision. So this is useful when we're combining float numbers. So I'll give you an example. So machine precision is defined to be the gap between the number 1 and the smallest number x tilde, such that x tilde is greater than 1. So what do I mean by that? I'll show. Okay, so let me go to the code directly. Okay, so this is the code. So what I'm doing here is let's say you take this small number 1 over 2 power 50, okay, and then you are adding 2 to it, okay. So when you add, so this is just this, so when you add 2 plus 1 over 2 power 50, so this is this value, okay. So this is this value, 1 over 2 power 50 divided by 2, so that's 1 over 2 power 51. So this is this, and when you add this number to 2, you will get this. You see there's some change, but then after that, if you add anything, so let's say when the number reaches this value, so if you divide it by 2 then, and you add again this to this value, you will get 2. It will not change, because here you are adding this value divided by 2 to 2 value. So because the number has gone smaller than this, so even if you just keep adding it, it will not change. So here I'm even halving that number. So if you 2 plus any number 2.2, any number smaller than 2.2 10 power 16, you will get 2 again, okay. So so this is how you calculate the machine precision. So at least this much error will be there. So now we discussed two important operations involving floats. We've already talked about subtraction before, and I will also talk about comparison. That so one very important rule, because comparison may get involved while you are taking while loops, for loops, or whenever you take conditionals. So comparison becomes important in those cases, and we have already talked about subtraction. So let me talk about subtraction first. So careful subtraction using floats. So I'll just give a feel for it through an example. Okay, so let's say that you are trying to evaluate the subtraction of these two digits. So both these digits have 12 significant digits, 11 or 12, anyway, some number of significant digits, and you know the number exactly. So this is what you get. So let's say you have this number, and this is the exact result that you should get. But when you do this, the same computation on Python, you get this instead. So this is this and this is this. And the reason is that because the Python won't be able to store both these numbers exactly, because these have 20 significant digits, and the Python won't store all of those significant digits. So explanation comes next. So when you take this number, for example, so Python won't store anything beyond 8. So I think this should be 16 of the 16. Okay. So depending upon the so here the Python won't be able to store any things. How should I say that? More than 16 significant digits for that number. Okay. So it will round it off. So here you can see that 1 is here, so it will match till 5, and then here is 6, and but it has rounded off whatever comes after 6 to 8. So this is the first round off, and that is causing the error. And similarly for this, so it has just chopped off these numbers here. So it has stored only, so although this has 20 significant digits, but it has stored only 4, 8, and 9. And when you subtract it, you will get this number. Okay. So it matches. So only 6 significant digits will match out of the 11, because it has 11 significant digits, and out of those only 6 significant digits will match. So that's why. So this gives you a flavor that you should be careful while you subtract using floats, and should be especially careful when you are introducing too many significant digits. The last one is comparison of floats. So machine numbers, I'm sorry, this is machine numbers. So let's say machine numbers are 2, 5, all integers, for example. They can be represented exactly, but not the floating point numbers, the real numbers, square root 2, for example, pi, for example. And but they are, when you store them, they are rounded off, as we saw in the previous slide. They are rounded off to the nearest machine numbers. Okay. So now if you were to make a comparison, so let's say you have xt, some term, which is equal to the sum of 0.1 and 0.3, and yt is 0.3. So when you check whether yt or xt are equal or not, you will get false. Although they are equal, you might say that they're equal, but it's because that the that these are not machine numbers, and floating point numbers are rounded off to the nearest machine number. So if you check what xt is, so xt is equal to this. It's not exactly 0.3, but this number. And yt is equal to this. So that's why it is giving you false. So so make it a practice that you should almost never compare to floating point numbers. So you might use them wherever you use conditionals, for example. So you should make a habit of never really comparing to real numbers or to floating point numbers. So the solution is to take something called as the absolute epsilon method. Okay. So what you do, you say that the difference between the two numbers here is less than some certain value. So here you have chosen that to be 10 to the minus 12. So that comes out to be true. So to that precision, they are the same. But because Python is not able to store the number exactly, it will not say that this number is exactly same as that number. But to that precision, let's say of the order of 10 to the minus 12, the numbers are the same. Okay. So now, finally, let me summarize what we discussed today. How much time do I have? Oh, I'm almost on time. Fine. So today we talked about error estimation, and first we motivated why should you be interested in estimating errors, and then types of errors. So in order to quantify that this is accurate as compared to that, so we introduced the ideas of relative and the absolute errors. And then we also saw that the errors can creep in because of many different reasons. One was human, the other one was approximate and rounding off. I mean, because of approximation and because of rounding off. And then we talked about error propagation, that if quantity depends upon many variables, how will the error propagate? And we talked about a special case of catastrophic cancellation, when the numbers that you're subtracting are very close to each other. So always be careful when you're subtracting two numbers that are very close to each other. So that might lead to a very large error. And then we talked about real number representation. So, and we talked about the ideas of over and underflow. So if number that you're storing in Python, or for that matter any program or any programming language, if it is larger than some certain number, it will give you infinity. If it is smaller than some certain number, it will just give you 0. And then about the machine precision. So machine precision was defined to be the smallest number that you that is larger than 1. That you can take, because the next number to 1 is mathematically not defined. So the notion itself is not defined. But that notion in Python program is defined that way, that so machine precision is defined in terms of a number that is next to 1. Okay, I think you're getting my idea what I'm trying to say. And the machine precision is the difference between the two. So if you add any number smaller than the machine precision, the Python won't be able to do anything about it. So it will just give you the same answer back. And then we talked about comparison of floats using the absolute method. Okay, so this is what I had to discuss about today. Thank you for your attention. If you have any questions, I can answer them now. So this was my first time. Okay, so my personal thing is that this might look